Morning and welcome to Kung Fu Physics, where we are working our way through the practice physics GRE problems one at a time. And today's problem is off of the 1992 practice physics GRE exam. It is problem number 6, classical mechanics problem. Probably several different ways to solve this problem. I'm going to be solving it very much in a freshman physics 101, just using a couple of free body diagrams. And that way really makes sense to me. I looked on the website that tends to have a lot of solutions that are written up for physics GRE problems, and they had something interesting for this problem called the method of sections. If you're in mechanical engineering, that might sound really familiar to you. It wasn't sounding familiar to me at all, so I thought, well, the method of sections isn't going to help me solve this problem. I'm going to do it the way I'm going to do it, and so I worked out a way to do this problem that I think is pretty straightforward, and there's got to be other people, other physicists out there that would look at this problem the same way that I do. So this is what it looks like just quickly. It's got a diagram, so turn to, if you have these printed off, test 1992 number 6. We'll go ahead and get started. As usual, I glance at the answers first. Looking at the answers, A and E pop out at me a little bit. A, because it does not have one of the variables, it's missing the mu. And then E, because it is one of these, kind of types of E, all of the above type of answers. It's sort of an interesting thing, a different description rather than an actual answer. So maybe one of those will pop out as either being the answer or will be readily eliminated, and there is nothing wrong on the physics GRE of looking at it as you are going through, and rather than trying to pick the right answer, you are going through and trying to eliminate as many wrong answers as possible, preferably 4 wrong answers, leaving you with the right answer. So nothing wrong with looking at it that way. Remember that. Go ahead and start the problem now after a quick glance at the answers. The figure, hopefully you can see that. Number 6, 2 wedges, each of mass lowercase m, are placed next to each other on a flat floor. A cube of mass uppercase M is balanced on the wedges as shown above. Assume no friction between the cube and the wedges, and a coefficient of static friction, mu, is less than 1. Between the wedges and the floor, what is the largest uppercase M that can be balanced as shown without motion of the wedges? So conceptually, really quick, we can sort of get a picture of what's going on. We've got these wedges sitting on the floor, we're dropping something heavy on top of it, and we can visualize the circumstances. If there's not a lot of friction between those wedges, we can visualize this thing pushing the wedges apart and falling through and maybe settling on the floor. But if there is a lot of friction, we could also maybe imagine that mass sort of balancing there. So conceptually they make sense. I think pretty quick you can eliminate at least one of the answers, being answer E. And I guess this is maybe dipping into a little bit of what I've heard described as the principle of extremes, imagining an extreme case. In this case, I would say imagine the mu being very close to 0. It says mu is less than 1, but imagine we select a mu that is very close to 0. So it is very much nearly a frictionless surface there, and we are going to put a really big mass on there, let's say. Black hole-ish big. We want a very heavy mass. So with almost no friction, are these little m, are these little wedges going to be able to stop this very, very big mass from pushing them aside and settling down? No. So the idea behind answer E is that all m will balance, I think, can get defeated pretty easily just using conceptual physics at that point. Long drawn out description there. Of course, on the physics GRE, if I worked that through my head and it made sense to me, I would be just taking my pencil and scratching that answer out and going on. So let's start. To solve this problem, I use a couple of diagrams, and I'm going to be taking quite a bit of little shortcuts in my head and they will hopefully make sense to you. So the first free body diagram, I have only a couple forces. The mass of this is a block with a big M, the block that's sitting on top. It has the two forces from the wedges acting up at 45-degree angles and its own mass acting down. I'm going to call these forces F. I guess I'll write up here. Now, summing the forces in the y direction, I'm going to set them equal. Let me put it this way. I'm going to set the forces acting down equal to the forces acting up, is the way I look at it. It saves me a step, and because the two forces are balancing out in those two directions, there is no acceleration in the y direction, which is what we want because we want the threshold. We want to find the mass that is just balancing there with zero acceleration. And so setting the forces acting down equal to the forces acting up, there are two of them, and what that force is actually is going to be the y component. And okay, I'll take a couple extra steps here, but I'm going to skip this step for these little trig bits. I'm going to skip this step in the next part, but I'll do it here. Of course, in the y component of that force is equal to the force times the sine of 45 degrees. And that's equal to F1 over root 2. And you get that by knowing your trig triangles pretty well. Identities, is that what I would call them? I don't know. In my head, this is what pops into my head when I am trying to recall what the sines and cosines are. Of course, you have to divide through and get the hypotenuse equal to 1 to get those, but for me, this just sort of makes sense. The 1, 1, 2, and the 1, in my head, I kind of think through it this way: 1, 2, 3. And I know where the square root goes, and then I have to remember where the angles go, which one's which, but 1, 2, 3, 1, 1, 2. These triangles, I'd never forget these, even if I forget exactly what the cosine or sine of 30 or 60 or whatever is. I can always come back to that. So if that helps you use it, if you have a faster way in your head, then do it that way. But so yeah, so I would say that mg, or m, I'm going to move the g over, m equals 2 divided by root 2 is root 2, so root 2 times f over g. Alright, moving on. The next free body diagram, I would do one of the wedges. I'll do the wedge on the right. It only has 4 forces acting on it. These are a reaction pair. This force and this force will also be equal to F. You have the mass of this wedge, little m times g. You have the normal force, N. And you have the friction that is opposing the force pushing this way. I will draw that in there. Now quickly, I would sum these forces in the y direction. Again, I would put the forces acting down equal to the forces acting up, because certainly the triangle wedge block is not accelerating up or down off of the table, so the acceleration in the y direction is 0. And again, I'm going to take a shortcut here. You'd be using the sine and blah blah blah, but it's basically f over root 2 is acting down plus little mg is acting down. They're equal to n acting up. Okay, and then I do some of the forces in the x direction equal to 0, because there's no acceleration in the x direction. Again, we're on that threshold. So again, I get f over root 2. And this is a little simpler, is just equal to mu times n. So I could go back up here and get what mu times n is. I just multiply that through. And so I can take this junk and move it down here, and I get f over root 2 equals mu f over root 2 plus mu mg. Okay, and I'm gonna try and do this in my head and not look like an idiot and screw it up. Because the more you can do in your head and the better you are at algebra, the better off you'll be on the physics GRE. I think I got that right. And then I want to take that and shove it back up into this. So basically I am taking f and moving this up there, and I can also kind of save a step in my head and just imagine this being there and then cancel what I can. The g is on the bottom here, the g is on the top here, so when I plug that in for f, those are gonna go bye-bye. I think that's all I can cancel. The root 2 times the root 2 just gives me a 2, so I write what m equals here. 2 comes out there, and then whatever's left I write mu m remains on the top and 1 minus mu on the bottom. I think I did that right. 2 mu m, 1 minus mu. Yeah, that's one of our answers. So I would go to answer D, would be the one that's looking like what I got there. Now, of course, when I do these problems, I work through them and kind of rehearse them. So not only do I not just screw them up or really take a longer drawn out time to explain them, but sort of do a simplified version of it. But I have to admit that when working through this problem, just shuffling my algebra around and stuff, all the stupid little root 2's and 2's coming around, I kind of screwed this problem up. And so I guess the take-home message of a problem like this is use shortcuts, work fast, but not at the expense of being careful. Because what happened to me is I worked through the problem and then I got an answer that I'm sitting I'm looking for an answer that's not one of my options. And then what do? I mean, you have the option of trying to hope you can go through really quick, race through, and find if you just forgot to distribute something in your algebra or something. You have the option of just canning it and starting the problem over from scratch. There are times when sometimes I think that might be the right way to do it. But it can be really frustrating when you're trying to knock this problem out in less than 2 minutes and you end up taking twice as long because you're going back and repeating the problem because you made a stupid little mistake somewhere. So that's what I want to say. Calculate fast, practice, 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 always working to do your algebra quickly and accurately and take shortcuts where you can get away with them. And that's it. Practice and study hard. See you next time.